Okay, so we get started. So in the second half, we'll look into the deep learning approach of the computer vision. So morning we looked at the classical computer vision where there is not any model-based learning that is involved in it. We looked at the fundamentals operations of image processing, like loading an image, displaying an image, and then converting from one color space to another color space. What is the significance of converting this color space? And then we touched upon some important image processing operations like such as thresholding, image filtering, etc. And one of the important operations that is used in image filtering is called convolution. And this is a natural continuation of that. You need a basic introduction of what convolution is or what does that mean in order to get introduced to a type of neural network that is specifically designed and applied in images and videos. And that is called convolutional neural network. Okay. So I hope you already have a background or a prerequisite completed that you have some exposure to what deep learning is, right? What is a neural network? Um, so deep learning is an evolution of the machine learning, and machine learning are a certain type of mathematical and statistical algorithms that are applied on certain numerical representation of your data. And then machine learnings are typically applied to do some sort of classification or clustering. And machine learning algorithms such as support vector machine, random forest, and XGBoost, or clustering such as k-means or any other clusterings like PCA. There is one important dependency or prerequisite that is there for these machine learning algorithms. And what is that? No, don't go too much technical. I mean, you have a data and then you need to apply these machine learning algorithms on this. Can you apply these machine learning algorithms on the raw data? Yeah. Yeah. So basically there is another term called feature extraction, right? So you need to do some feature engineering. So you have a data, you do some EDA, that is explorative data analysis, to understand what that data is, what is the distribution of the data, what type of data it is, what categories of data is, what will be a suitable algorithm that can be applied here. But then once you decide, okay, this is a classification problem, I want to classify the so-called floral types, right? Some iris centosa data set, right? Uh, so you already completed machine learning. Okay. So you had this iris centosa problem. Yes. Okay. And then the raw data is basically a vector of numbers, right? But then can we apply an SVM or a random forest on that? Probably not. you need to do some sort of feature engineering. Probably you need to convert that and do some normalization or something like that. Um, and probably if that is not sufficient, you do some more data transformation like polynomial transformation or logarithmic transformation, right? So these are things that are hand engineered by the data scientists in order to make suitable for that machine learning algorithm to get the best performance of that model, right? So this is called feature engineering. Um, so when it was before the deep learning, when the machine learning was applied onto the images, the first prerequisite mandatory step is to you need to convert the raw image into features, right? Those features are mostly edges, and some areas or some sort of a morphological extraction of those images, like the area or any sort of geometrical representations. Okay. And there is also some advanced feature extraction methods, something called a SIFT, scale invariant feature transform, SIFT. So what that takes is it takes the raw image, converts that into grayscale, converts that into edge image. Then from that edge image, it extracts some features and stores them into some sort of a vector representation. And on that vector representation or the features, we apply machine learning such as SVM or random forest like that. So this was before 2000 something like that. So there used to be a famous computer vision competition was going on from Stanford, and it's called ImageNet. Okay, so they used to have sort of lakhs and millions of images categorized into some thousand classes. Okay, the challenge is researchers from all over the world, from the top tier one universities like Stanford, MITs, like that. So they used to compete. So they used to build some new algorithms, and then they will get to beat that leaderboard. So whoever is trying to get the best performance, they come as the top and they publish papers. Typically, this is what they do. So they take images, they apply some sort of SIFT, and then they apply some machine learning algorithms, and then they run it on some test data set, and then they publish the leaderboard. Okay, they were touching around 70, 75, something like that. I don't know, I'm just making up a number. But suddenly in 2012, everything changed. There was a guy called Alex, right? And he invented a special type of neural network called CNN, convolution neural network. And he did a big jump, big leap forward, and then he outperformed all other previous types of algorithms, and that is when this revolution started. So in 2012. But did Alex invented the CNN? Not really. It was, see, there's a lot of controversy who invented this, but as far as I know, there was a person called Jan LeCun. You remember? You don't know? Okay. So he was the previous Meta AI head, but now he started his own company. So he used to work in Bell Labs, right? At that time, he invented this. Convolutional neural networks. It was in 1970s, 80s, like that. So there are some videos also. So he invented for number identification. So 0, 1, 2, 3, 4, 5 up to 9. So if you put one number, it will tell you what number is that. Very toy example compared to what we are now. But at that time, it was the breakthrough, right? Then after that, it didn't develop much because of there's an inherent problem with the neural network that it is very compute heavy. It needs a lot of compute power to do training of this model. That is when this gaming industry developed. This NVIDIA guys developed this GPUs, and AlexNet used that parallel processing to efficiently train as a larger neural network. And then he proved that it could outperform all the previous machine learning models. That is when the deep learning era started for applying a neural network for images and videos. Okay. Um, so in CNN, there are different layers in CNN. So of course, it starts with an input layer, which takes in an input image. Then the final layer will, depending on the problems that we are addressing. Okay, it could be a classification layer, or it could be some sort of a dense prediction layer. For example, the segmentation that you are talking about. So it will not have either classification, a binary classification like a cat or a dog. It will have the same output as the input. I mean, if we have an input image of 32 by 32, the output will also look like a 32 or 32, and each pixel will have its different classes. Okay, that's, we call it as dense prediction. So in between, there are different types of layers, and the most important layer is called as convolutional layer. And what does this convolutional layer does is that it applies a special filter called kernels. The filters and kernels are interchangeable. Some call it filters, some call it kernels. Okay. And the main purpose of these filters or kernels is to um, extract meaningful features from the images. And these meaningful features are not just built in just one go. They are just built over a continuous different layers, right? So it's the more, the deeper the model is, the more the number of layers is. And for every level of the model, it extracts a certain types of features. So the first initial, it will extract more high level features like or low level features like edges, lines, and all those curves and all those things. But that doesn't make any meaning at that point. They are just edges and curves and lines and things like that. As it progress, all these edges, lines, and curves, they all build together. Then they slowly stack upon each other. So the edges then becomes a shape. They give a shape like a face, a hand. For dog and cat, they have different shape, right? So then they are used to identify each individual elements of the whole objects. First, it will be very lines, curves, and things. Then these lines and curves, they join together, they forms eyes, nose, tails, legs, like that. Then these eyes, hands, legs, tails, and other features, they all combine together. Then they form the actual object like a cat or a dog. So this is how it progresses. Then finally, based on the final layer feature set, the model will make a classification whether it is a cat or a dog. Okay. So essentially, in one line, we need to extract meaningful features. But how do we do that more reliably, accurately, and effectively? It's up to the how we design these layers. Okay. So the main, the core of all this is the convolutional layer. But uh, what happens is, if we just apply convolutional layer, it becomes too inefficient, because the size of the feature map is like, it will become huge, because it is like 1,000 by 1,000 images. It will be like shown getting out of memory. So in order to also, we also be compute efficient, we need to also downsize it or compress it, so that we can handle this computations in an efficient way. So that's why they added layers such as pooling layers, which means if you have 10 cross 10, they just reduce it by half and make it like 5 cross 5. So after doing a lot of experimentation, they found that either you do it 10 cross 10 or 5 cross 5, this 5 cross 5 is able to retain most of the important information that is there in the original size. So as long as it is retaining the origin, the key informations, it is better to downsize this so that the computations becomes very efficient. Otherwise, it will take very long time for processing. Also, it needs a lot of computing power. Okay, and just before the final layer, uh, we need to flatten these feature maps. The feature maps still before the final layer, it will be in a matrix form. Now you cannot apply a classification directly on a matrix. First, you need to flatten it and make it into a vector. Then only you can apply some classification layer on top of this flattened vectors. Okay. That's why what is the purpose of fully connected layer? So we have, again, this is a very high level and basics. There's a lot more detail, but if you get this basics through, then on your own, you can explore more and more, and then you can build upon this. Okay. So it starts with an input layer that takes in and raw input image, and then it applies different levels of convolutional layer, and then it also applies pooling layer. So the pooling layer is mainly to reduce the computation, and then it tries to retain the key information as much as possible. And then finally, we need to flatten these feature maps so that we can apply a classification on this fully connected vector, and then get the final output. For example, it could be a binary classification such as cat versus dog, or it could be a dense prediction such as a segmentation map. Okay. Any doubt in this? I know this slide has been condensed and it covers a lot. Okay. Now, there was one uh, website. I found it very useful and interesting and intuitive to understand the CNN for beginners. Probably
how we decide how many layers we should have, like how many partition layers we should have on the
Yeah, that is a good question, but there is not any standards, but whatever the previous research guys they did, that sort of a trend follows. So typically, if you see right in this also, it will have one layer of convolution and then followed by one layer of pooling layer, and then there will be another layer of convolution, another layer of pooling. So likewise, this convolutional pooling will be keep repeating. And so the AlexNet or not AlexNet, I think there was another network called VGG, which comes from the Visual Geometry Group of Oxford. That's why it's called VGG. There was no standard before that. Everyone has their own approach of how they design this one. So some they will form a certain structure layers. Another guys will do a different structure layer. There is no any hard and fast rules to do it, but they are best practices like a pooling layer will follow a convolutional layer, and finally there should be a fully connected layer. Okay, and then initially the depth of the neural network was somewhere around 50 layers, but then slowly it was growing like exponentially. Some were using 150 layers, some were using 500 layers like that. So the more the deeper, it become more the accurate. But the more the deeper, it also needs lot of data. Yes. So you have to also be careful that you are designing in such a way that it is not overfitting. So you can create a very big neural network and also very deep neural network. But if your data is only 100 images and then just only 2 classes, it will be easily overfitting. So if this website is a good for any beginners to understand what is going under the hood in a convolutional neural network. So here also you see there's a pattern. So there is an input layer which takes the image, and there is a convolutional layer, and then there is an activation layer. So always each deep learning layer will have a convolution layer followed by an activation layer. So activation layer can be ReLU, GReLU, those kind of things. So again the same. So there is here, if you see, there is 2 convolutional layer followed by 1 max pool layer. The same, another 2 convolution layer followed by 1 max pool layer. Finally, there is 1 output layer. Okay. So this is a very tiny VGG network. So the VGG only came with this repeated pattern of 2 convolution, 1 max pool, 2 convolution, 1 max pool. They can repeat this how many number of times we want. If it is a very tiny, we just repeat it twice. But let's say if you have a very huge data set and if you have a very complex data set, you can repeat this, let's say 100 times. So now if you see, there are, sorry. Yeah, so here is where the probability score will be applied in the final layer. The softmax will be applied here. Okay. Okay, so let's understand what does each layer of the network do. Input layer is basically, it takes in an RGB image as input, and the input layer has 3 channels corresponding to the red, green, and blue. So we take and draw input image, and then we separate them into 3 channels, and then comes the convolutional layers. So what does convolution layer does is it applies a kernel onto the image and it extracts features that distinguish different images from one another. Okay, and this is the main goal of the CNN in order to extract meaningful features. Okay, and the kernel, right? So the kernel is something like a 3x3 kernel. And this 3x3 kernel is what will be learned during this training process. Initially, these kernels are initialized as a random set of numbers, but during the training process, these kernels are updated and they are optimized and fine-tuned in such a way that the model is able to do its assigned task accurately. Okay, that's the goal of this entire CNN training process. Now, what does convolution means? So convolution is basically take a 3x3 kernel and apply that kernel onto the entire image. Okay. See, for example, here is a 3x3, and what it does is it just plays on to the image, scans the image, does a element-wise multiplication of the pixel values and the kernels, and the sum of the product will then be put into the new image. Okay, so here you can see there is uh, gray sort of numbers are dynamically getting updated. Those are actually the pixel values, and the bottom ones are the kernel values. Okay. Now what happens is, as we just scan, the pixel values are element wise multiplied by the kernel values. They are then summed, and the sum is then transformed into the output matrix. The input is a 64 cross 64 matrix. The output is a 62 cross 62 matrix. Okay. Now, as you can see, the dimension is reduced by 2 cross 2, right? So 64 cross 64 becomes 62 cross 62. There is also a mathematical calculation of how this size is determined. But you can intuitively understand from this. For example, if the input image is 5 cross 5, and if you have a kernel of 3 cross 3, then your output becomes also 3 cross 3. But in some cases, we intend to retain the same input size. In order to do that, then you need to do something called as padding. Okay. So if I add 1 cross 1 padding, so padding is nothing but it adds 1 pixels around to that 5 cross 5 input matrix. Okay. So now it becomes like a 7 cross 7 matrix. If I do a padding of 1, then the input 5 cross 5 matrix becomes 7 cross 7. And if I convolve with the kernel of 3 cross 3, then I retain the input dimension, and then now my output will be 5 cross 5. Okay. Again, if you increase the stride also, the output dimension will vary. So instead of striding 1 pixel at a time, if you see, right, I'm striding 1 pixel at a time. So now I am here. If I move right by 1 pixel, I strided by 1. Then if I move, I strided by 1. So this is stride of 1. If I move down, I move by 1 pixels. But you can also stride by 2, which means if I am here, if I move, I jump 2 pixels. If I move here, I jump 2 pixels. If I move down, I jump 2 pixels. In this case, my output dimension will also get reduced significantly. If I increase my stride, my output dimension will also reduce. Okay. So these are the different terminologies that probably you should at least be aware of what it is at a high level. A more detailed understanding when you spend a lot of time in this, I think you'll come to know. But at least remember a padding, what is kernel size, what is a stride. These three things are required and for to design your convolutional layer. So when you design your convolutional layer, these three things is what you need to specify. Your padding, your kernel size and stride. By default, it comes with the 3 cross 3 kernel, padding of 0, and then stride of 1. But if you want to design apart from these default values, you can just play with these things and see how your model training goes. Okay. And these are in called hyperparameters because these are all user defined. So in deep learning, we have two types of parameters. One is model parameters. Another one is hyperparameters. Can someone say what is the difference between these two? Sorry, can you be a little louder?
Previously defined.
What is model parameters?
Features are being hyperparameters are only important features where it differs out to differs. When you modify or when you fine tune, when you update the weights, the output differs are different.
Yeah, somewhat closer, more precise, simple explanation. So when you say model parameters, if these are model features, what is it technical? So, yeah. So model parameters are nothing but the weights. So the weights and bias, and model parameters are those parameters that are learned and updated during the model training. Okay, and these are not user defined. These are all learned during the model training. Okay, but hyperparameters are those are user defined and they are not learned. They are just defined by the users, and then they are just um, uh, tried with the different values so that we try to find the optimal to get the best performance of the model. Okay. So do you understand what is feature map from this? So come on, tell me what is feature. Hmm?
Apply feature on top of that, they are extending the features.
Mhm.
And all the features we give in another matrix,
Mhm.
there is a feature map,
Yes.
which have the whatever feature they are extending,
Mm.
those informations are there inside that feature map.
Yeah.
That we apply the activation function.
Yes. Yeah.
Then we do max pooling,
Yeah.
pooling, average pooling on top of that.
Yeah.
And after max pooling, we do whatever after max pooling, we are according that you are body vector
Okay. Finally.
finally.
Yeah.
And then we pass it to our neural network.
Top match layer.
So neural network,
Oh, another fully connected layer. Okay.
then output we
Yeah. Yeah. I think. Yeah. You could try, but these are all already tried and sort of standardized. Mostly this what will work in most of the cases, but that doesn't mean that this has to be the order followed. But I think previously they have tried with the different combinations, and this is what is mostly recommended.
Here the deep learning topic when I was studying.
Yeah.
Somewhere I have seen this feature mapping things, but
Yeah.
telling that it automatic. When you don't have
Yeah.
to map, whenever you will do that survey map, automatic some feature will map it only this corner edge. This will only the mouth. Okay. This how is it means automatically that I wouldn't understand.
So basically, we design a neural network and then we initiate these kernels with some random values. And then we pass in a batch of data which is already labeled. We know which is cat and which is dog. And then first it just passes all this batch of labeled data into these layers of neural network. And then the model will just do some random predictions. Probably 80% of that batch of data will be wrong. It will say dog as cat and cat as dog. Okay, in the first pass. At that time, they will calculate a loss. and then those laws are then back propagated. Then we update the kernel weights. This process happens for hundreds and hundreds of cycles. Finally, at the end of these iterations, the model will adjust these kernels in such a way that it is correctly predicting the cat as cat and dog as dog. If it does some mistake, it will be penalized, and these penalized will be then back propagated to update these weights. It keeps adjusting these weights up plus like that until it fine tune it and make sure that it is predicting it correctly. So this is what it does. So you just design a neural network, pass in a data. That's it. You just train it for 100 cycles and more. Then at the end of that iterations, it will learn the features automatically. And again, it is more of a black box. It's very difficult to explain how these things are learned. But high level understanding is what you explained. Initially, it learns those low level features like edges, lines, curves, like that. And then at the end, it learns all those connected informations like eyes and tails and hands, like that. So here also you can see, right? So here it's more like edges, but as it goes deeper and deeper, it learns more high level features. Oh, yeah. So this is the feature map. So this is how the feature map is built. So we have one kernel that is scanning the red channel, one kernel scanning the blue channel, one kernel scanning the green channel, and these are then just concatenated. Okay. Um, okay, I hope you're following. And then there is a ReLU activation layer. We take this feature map and then we apply the ReLU activation, which is nothing but make all the negatives as zeros. Same thing repeats in every layer. But finally, in Maxport, this is what will happen, right? You can see that for every 2 cross 2, whichever is the maximum, that value is then put it into the output layer. So now you see if you take an input of 60 cross 60, and if you do pooling by 2 cross 2, the output reduces by half. So this is basically a significant dimensionality reduction, which helps in speeding up the process. And this is what happens in the final layer. So after the feature map, we just then flattens them, right? So now 13 cross 13 into 10 will then become 1690 vectors. Okay. Then we apply softmax on that. So softmax is mathematically is what is doing here. So it takes applies this formula, and then what it does is that it basically tries to maximize the probability of that correct class and tries to minimize the probability of the incorrect class. It does some sort of a normalization. so that it pushes the correct class towards 100% probability and the other ones towards the 0 probability. So in this case, the red panda is what gets the highest probability. So it gets about 95.7%. Rest everything is less than like 0.5%. 5%, sorry. Okay. So you are aware of activation functions, right? Softmax, pooling layers, flattened layers. I think that's all basics of CNNs. PyTorch. Yeah. Sorry, yeah, PyTorch features. So then PyTorch we need to learn separately or PyTorch? Yeah, PyTorch we need to learn little separately. But I have a very crash course on PyTorch. We'll go through that. Okay. So now we understood what is CNN. Before going into image classification using PyTorch, probably we'll take a quick crash course on how to use PyTorch, and then we'll move on to how to apply image classification using a deep learning model in PyTorch. Okay. I can share this link. Okay. So PyTorch is an open source deep learning framework, and it is developed and maintained by Meta or previously Facebook. There was always a very popular question where if we should prefer TensorFlow or PyTorch. I think TensorFlow was the first deep learning framework, and it was developed and maintained by Google, and it's also open source. But of late, I think most of the recent models are PyTorch based because PyTorch is most preferred by the researchers. There used to be opinion that TensorFlow is more for deployment and PyTorch is for more for research purpose. But then I think nowadays, even for deployment and production use, also we are using PyTorch. There's might be very specific reason you might use TensorFlow. For example, there might be a model that is available only in TensorFlow, and that model is what is the best for your particular use case. Then you might go for a TensorFlow. Otherwise, I think PyTorch would be the general purpose recommended framework for computer vision deep learning. That's why I asked in some job profile. In description, they have specifically mentioned they need PyTorch. Okay. Yeah, yeah. So, yeah, I mean, if you know the fundamentals and if you're already familiar with TensorFlow, with a little bit of interest and effort, you can switch to PyTorch. Okay, so it's a very high level introduction to PyTorch. This is not a very exhaustive in detail course on PyTorch, but at least it will give you a get head start for PyTorch, and probably you can explore more in your free time.
PyTorch will be concept of many different. Both are two different frameworks, but
Yes.
any advantage, disadvantage.
Again, there are different mixed opinions. It depends on see for I started with TensorFlow only, and then TensorFlow 1.0 was had a lot of complexities involved in it. It was not intuitive. It was more of designed in a software developer's perspective or something like that. It was not very data scientist friendly, and they did not had a very popular thing called eager mode, which means first you need to build a compute graph, and then you need to compile that graph, and then you need to pass the data to that compiled graph, like a lot of complexities. I mean, for a data scientist who is focusing on solving a problem, it was little bit overhead for him to learn all these low level complexities. So then everybody sort of moved towards PyTorch, which had an inbuilt eager mode, which is more of a data scientist friendly framework, so that they can just focus on solving a problem instead of trying to become a low level software engineer. Okay, they are like two different guys. There are very few guys who can live in this intersection, but they are two sides of a Venn diagram. So that is where majority of them they went into PyTorch. Then TensorFlow Google guys realized they made a mistake, and then they also shifted towards this eager mode, which was already developed outside of TensorFlow by Keras. So there was a guy called Francis. So what is his name?
But Keras is not a separate package, right? It's a part.
Yeah. After that, what happened is it used to be Francois. So Francois, a French scientist, he understood the TensorFlow problem, and he built a framework called Keras on top of TensorFlow, which was writing like a lot of abstractions. So a lot of people were using Keras. Then in 2.0, Google integrated TensorFlow and Keras, and they offered Keras in TensorFlow itself. So you don't have to go and separately install Keras. And then the gap reduced, but the researchers they continued to use PyTorch.
Again, but this MCU and small embedded devices have
Again,
TensorFlow, like they don't have the pipe.
this is what the typical they claim it, but again, if you're going very low level, probably there are certain advantage with TensorFlow, like what you mentioned. But otherwise, generally, we prefer PyTorch. Okay, so then, so how do you install PyTorch? Basically, go to PyTorch and then click Get Started. So this command, right, pip install torch vision. This will typically will work. I think you might have already done this, and that PyTorch is already installed in Collab, so I'm not doing that. So PyTorch, so in deep learning we use vectors. So vectors are one-dimensional numerical representations. After vectors, we have matrix, which is a two-dimensional representation. So tensors are something, it's similar to matrix, but they also have a lot more dimensionality possible than just two dimensionals. Okay, so that's why they called it as tensors, and they are not matrix or arrays. But for simplicity, you can just assume that tensors are similar to matrix or n-dimensional arrays. So tensors are the fundamental data structures in PyTorch, and similar to NumPy arrays, but with an added capability of utilizing GPUs for faster computations. Okay. Now, if you want to define a basic data structure, so what you call is starch.tensor, and we can say 1, 2, 3. Okay. And this is how it will look like. So in this, you can do the same thing what you can do with NumPy matrix. You can do slicing, indexing, all those things. You can do multiplication, addition, all those different things you can do. And then the second important concept is called autograd, which is basically in deep learning. If you already know the fundamentals of deep learning, so we have a forward pass and then we have a backward pass, right? So in the forward pass, we pass the data through the layers of the neural network. We then compute the loss, and then we apply a gradient. So we apply the loss and then we calculate the gradients, and then we back propagate the gradients. So calculating gradients is a very important step in training a deep learning model. Okay. Now this calculating the gradients is inherently built within PyTorch framework. You don't have to implement your gradient calculation on your own. Whenever you say backward, the gradient calculations are automatically calculated for you. Okay. So the autograd package in PyTorch automatically computes the gradients for tensors involved in a computations. This is particularly useful for implementing deep learning models where back propagation is necessary. Okay. Now let's look at a very basic autograd example. In these examples, we create tensors. Now what we have done is we have created an input tensor called X, and then there is an weights tensor called W, and there is a bias called B. Now this is what a single neuron will look like. A single neuron is nothing but Y is equal to WX plus B, right? You know that, right? Now this is what a computational graphs looks like. So when you say Y is equal to W into X plus B, then if you do Y dot backward, which means it will automatically calculate dy by dx, dy by dw, dy by db, which is necessary for me to, these are the changes that is required for me to update w and b. Okay. Yeah, bias is gone.
So we don't have to.
Yeah, we don't. Only weights we update. Bias also we update. Okay. Yeah, weights and bias are basically, I think, model parameters. So for each neuron, each feature map means each kernels. If you're talking about
One of the edges are image. The small segment of the image. So that is featured.
yeah. So here you can understand better. So here, right? So this kernel, right? Whatever is passing through it, which is a small window, that is basically the weights. So it has a 3x3 kernel. So it has 9 weights that has to be learned during this model training process. Then we have a bias that will be added after we are doing this convolutional operation. So convolution operation is basically element-wise multiplication of these kernels with the image, and then we add the finally bias, and that becomes my output feature map. Output feature map, but there are 3 kernels I have to learn for 3 channels. Yeah. So there is one kernel for red, one kernel for blue, one kernel for green, and each kernel has 9 values that I need to update or learn. So which means 3 into 9, 18 weights I have to learn. So that 18 values is basically updated. Initially, it will be some random values, but once it passes through the final layer and comes back, these 18 values gets updated. It just gets adjusted. So how much to adjust? That is where is determined by the gradient computation. So it takes the loss. If the loss is big, then the gradients is also big and the update is also big. So as we learn and learn and learn, the loss gets reduced. Towards the final, the adjustments becomes very micro, small adjustments only we make. Yes. No, not each layer will give it. What do you mean by each layer?
Each each remember
No.
this kernel slides over the image. So
See, there is one feature map. This is one single feature map that is derived from the 3 channels of the input image. And there are 3 kernels applied separately for the each channel of the image. Yes, yeah. So we have in this, see in this we have 10 feature maps are there. So basically, which means um, uh, so here there is not a concept of neurons because it is a convolutional neural network. So here we have a concept of kernels. So we have 10 kernels. So 10 kernels will result in 10 feature maps. You understand, right?
it is part of the
Yeah. I may not be very accurate in my explanation, but at least you get a very high level understanding. But probably when you read along with some textbooks, probably you'll understand. I might make some mistakes here and there. But at high level, there's a kernel, and these kernels are used to extract feature maps from the image, and each kernel has a uh, feature map. Okay. And whatever the weights that we are talking about, those weights are nothing but the kernel values. And these kernel values or the weights are gets updated using those gradient computations. For that only, we need this autograd functions from the PyTorch. Yes. Yes. 10 3x3 kernels will be there. Then let's say 10 into 3, 30 weights has to be learned during this process. Are you clear or I'm a little bit confusing? Okay. Then, yeah, the explanation is that see, when you define PyTorch tensor, you can pass this argument requires gradient is equal to true or false. Okay. Now, what happens is that by default it comes true. Okay. Now there is another later you will understand that sometimes we freeze certain layers. You know, right? So at that time you should say that request grade is equal to false, which means that there will be no any gradient update for this particular layers. So if you put gradient equal to true, which means that you are telling the PyTorch to track the gradients and update. If it is equal to false, it means it will no more update it. Whatever the old values, it just uses that again and again. So here there is, don't compare this with the actual neural network. For a demonstration purpose, I put everything is equal to true. So this is, these three are part of the computational graph, and then I put all these things to be true. So which means that all this might get updated. Yeah. Again, yeah, don't compare this with the actual implementation. I'm just okay. So let's say now you have PyTorch. Now, if you want to um, build a neural network, then you use a module called NN of the type torch. Okay, within the torch, there is a module called NN. Okay, so NN stands for neural network. So torch.nn is where all the different neural network layers are defined. So there can be linear layer, there can be convolutional layer, there can be max pool layer, fully connected layers, all those things are within the NN layers. Okay, this is what you will be most frequently using it. Now, let's say you have a random tensor called of a dimension 10 cross 3 and y 10 cross 2. Then you can define a linear layer taking 3 as your input layer and the output will be 2. Okay. Then you pass this input x into this linear neural network layer, and that will be your prediction, which means it's otherwise called as forward pass. So you have your input, which is 10 cross 3, and then you define a neural network layer where your input is 3 and output is 2. And then you pass the input x into the linear layer and you get the output. Now you compare this output with the y, which is an actual output. Again, this is an imaginary example. So now I can calculate my loss by getting the model's output and the actual output y, and then calculate the loss, and then I can do a backward propagation on the loss, and this will basically updates my weights in my linear layer. Got it right? Nice. Great. Yeah, that's all I've done. So this is how the basic building block of PyTorch will look like. Okay. If you are already familiar with TensorFlow, you don't do this in TensorFlow. Okay. But you can appreciate that the PyTorch gives you a very intuitive understanding of how taking things step by step. Uh, Yeah, we can continue after the break, I think. Yeah.